Right. Now, remember that the last one day we have finished talking about Einstein's field equations, and I have told you that so we are going to discuss some of the applications, like the things that we can do using these field equations and some other applications in general relativity, right? Now, today I am going to talk about Schwarzschild metric, which is a special metric that you can use for, very close to the black holes and those kind of situations. And you know that normally what we do in Einstein general theory of relativity is you have to define the metric, and then from the metric you can find the connection coefficients, and then the Riemann curvature tensor, Ricci tensor, and Ricci scalar. Right? So once you have all these things, and with the energy momentum tensor, you can write the field equations, and then you have to solve it, right? But I mean, solving field equation means you have to, solve set of differential equations. If the time permits, we will do it at least for one. But for this particular situation, so what I am going to show you here is how you think about defining a Schwarzschild metric like this, and at the same time, some of the applications of it. Right. So two major applications are gravitational time dilation and gravitational redshift, which I will be talking today. Right. So let me. Now, Einstein field equations are set of nonlinear differential equations, and these are not easy to solve exactly, even though we know the field equation not straightforward. So what Einstein did most of the time is he used approximations to make these predictions in general relativity, right, which are very accurate. And in 1916, this is kind of the same time where Einstein derived, field equations around 1915, and then the following year in 1916, there was a German astrophysicist called Karl Schwarzschild. So he published an exact solution of the field equation, right? Now his exact solutions were based on the Schwarzschild metric. So that's why we are going to talk about that. And so what he explained is that he has this metric called Schwarzschild metric, which explains a static, spherically symmetric gravitational field in an empty region of a space-time, right? Now, this is somewhat applicable for space-time near massive spherical objects, such as black holes, right? So this is why this particular situation is important. Now, we are going to discuss the form of the Schwarzschild metric and how we can derive it, and also some of the applications such as gravitational time dilation and gravitational redshift. Right now, for this one, so let's look at how the Schwarzschild metric looks like. Now, so once again, the reason for this approach is for any problem, you have to define the metric first, and then you have to go to find the connection coefficients. Because once you find the connection coefficients, you can find the Riemann curvature tensor, Ricci tensor, and Ricci scalar. And as you know, in the Einstein field equations, the left-hand side, you have the Ricci scalar and Ricci tensor and Ricci scalar in the left-hand side with the metric tensor. And on the right-hand side, you have the energy momentum tensor. So once you know those components, you can write the field equation and solve it, right? So that is the idea, right? Now his Schwarzschild metric has the form like this. And by the way, this dollar sign shouldn't be here. It's a mistake. So let me see whether I can check that function. That should be an extra dollar sign. So that should be here. right? So I have made the correction, so I will upload the corrected one. You can see that this is the metric. As you know that for the other situations we have discussed what is a metric. So it has the form 1 minus 2gm over c squared r times c squared for the time component, and for the special component for the r, theta and phi. So you have dr over 1 minus 2gm over c squared r, and then r squared d theta squared r squared sine squared and d phi squared, right? And then there is a way that we can verify that these components are correct for the Schwarzschild metric, and I will discuss that with you. And there is a section that I am going to assign you to work with, and this is specifically to practice with this, finding these connection coefficients and the key tensor, Riemannian tensor, those kind of things. Now here the m is the mass of the spherically symmetric gravitational source. For example, if we have the sun as the gravitational source, this m will be the mass of the sun, right? And g is the gravitational constant, and you know about that from the Newtonian gravity. And these four coordinates, time, that is t, and then r, theta and phi, all these four components are called Schwarzschild coordinates. And we can actually write, and also astronomers used to write in this Schwarzschild matrix in different forms, right? One of those forms are, if you get small m is equal to gm over c squared. So that is this part. You have gm right here and c squared right here. So that whole term gm over c squared can be replaced from simple m, so that you can write the same metric just by changing the variables in this way. Now instead of having gm over c squared, you have simple m right here at this particular position, and here as well, right? So these are just, different forms that we use at different situations depending on what we are doing, right, with this metric. And the metric can also be written from in terms of this quantity, which we call as Schwarzschild radius. And if you have joined with the general degree lectures, remember that I have directly given this equation Schwarzschild radius to them, but this is how it comes. The Schwarzschild radius is defined in the Schwarzschild metric in this way. Now you have 2gm over c squared term here. That whole term is called as the Schwarzschild radius in this metric, right? So that's what I have done here, and then you can take 2gm over c squared and substitute a value for it, right? So that is rs, Schwarzschild radius, so that you can write the Schwarzschild metric in terms of Schwarzschild radius. So you just replace the terms, right? So there is nothing special, right? But this the Schwarzschild radius is important for black holes, as you know. That is the radius where you can reach to a black hole, and if you cross this particular point, then this is called actually event horizon. If you cross this particular point, then you cannot return back, right? So that is the idea. But here in the mathematically, you define it as 2gm over c squared, and I would even remember it. It is a component that comes again and again, even in this lecture, right? And once you have all these components, you can write the metric, so which has this form, right? So I have not done anything special. So all I have is these four components. This component for the t squared term, and then for the r squared, you have 1 over that same component. Then you have minus r squared sine squared theta, right? Because you only have, d theta squared, dr squared, d theta squared, and d phi squared terms. you have only the diagonal terms in this metric. All the other components are 0, right? So I guess this is clear for you. Now, when you have this metric, there is a small mistake here. This should be 1 minus. In this metric, we should have here 1 minus, not only 1. Right, so it's corrected. So you will receive the corrected version. Right. Now, when we derive this Schwarzschild matrix, there are some assumptions that we made. Those assumptions are mentioned here. The number 1 is the metric describe the geometry of the space-time surrounding spherically symmetric body. Right? So we assume that when we derive this spherical metric, this metric describes the geometry of space-time around a spherically symmetric body. Now, for example, we assume that for a particular star or a planet has this spherical symmetry, right? So which means for each side when you look at, it look like the same. And the gravitational field is static, so which means we don't need to make things complicated with having time dependence gravitational field. So what we have done here is we have assumed that gravitational field will not change with the time, right? So that is the second assumption when we use the Schwarzschild metric. And then third one is the gravitational field is also spherically symmetric, and you will see that how we are going to use these different assumptions. And the metric is asymptotically flat. Now, since I need to make sure that you understand what that means, I have mentioned it inside the brackets. So what this means is when you have a spherically symmetric mass, and if you look at the metric at a very large distance from that particular mass, we assume that this curvature goes off and the space will look like flat. So this is a far away distance from this spherically symmetric body, right? Now, if that is the case, when you go for example, let's say you make the r goes to infinity. So that means you are looking at a far away distance from this spherically symmetric body. And if that is the case, this metric should be reduced to the Minkowski space metric or for the flat space, right? So that is what I mean from this word called metric is asymptotically flat, right? Now, when we use spherical symmetry, we normally use spherical coordinates, right? So all of you know that. And this is why the metric is written in terms of r, theta, and phi coordinates and the time part. And so if we want to satisfy these above conditions that I have made, we have defined a metric that have this following form, right? So this is based on that we need a spherically symmetric condition, and we are going to use spherical coordinates due to that reason, and we should have a time component. And initially we define the metric should have this form. So remember that what I am discussing here is how we can define that Schwarzschild metric. I already gave the form of the metric, but to have this form, somebody has to think and come up with the way of, somebody has to prove that, no? So what I am trying to discuss here is how you can assume the conditions and then approach to that particular metric, or how you can prove that it is the correct metric, right? Now, one reason that actually I am talking about this is this has some applications of finding connection coefficients and this key tensor and the key scalar, which will give you a good practice of applying those things. Now, initially, we define this form of the metric in this way, and we don't know what U means, and we don't know what V means, and what W means. Right? The reason for having this form is that we assume the spherical symmetry, so that we know that you can write in terms of R, theta, and phi. And these three functions, U, V, and W, initially we assume that they are functions of R. And then if we set W to be equal to 1, this is a derivation that somebody did, and we are just discussing it, right? So that's why there are some specific things that if we assume that W to be equal to 1, then you can rewrite that equation ds squared in this way, as you see in this equation 6. Instead of U and V, now you have A and B, right? So the reason is that when you set W to be equal to 1, remember we told that U, V, W, all of them are functions of R, and when you set the W to be equal to 1, the R's that you see in this equation 5 and equation 6 should be different R's, right? Because that setting W equal to 1, which we have taken as function of R, should change the other functions, right? So that is the idea. So which means now you have two new functions, A and B, and those are functions of R, but this R is not the same R as before, right? Right. So one thing that, according to our assumptions, what we have is, remember that this should be also asymptotically flat. So which means when R goes to infinity, that is when it goes further and further out from a spherical body, your metric should be reduced to the Minkowski space. So let's see whether having this, information, whether we will have that condition. So our assumptions, what should happen is when R goes to infinity, both these functions A and B should be equal to 1. Because when it equals to 1, you can see that this A will be equal to 1 and B will be equal to 1, so that you have C squared dt squared minus R squared, R d theta squared, and R squared sine squared theta d phi squared, which is the normal spherical coordinate system for the Minkowski space or for the flat space, right? So that's what I have mentioned here. And another thing that I have already mentioned, the R in the above equation 6 is not the same as in equation 5, right? So you have R in this equation 5 and also R again in this equation 6, but this R is not the same as this one right here. That is because you set W to be equal to 1. So which means you change the equation so that the other functions should change. So that's why we take, instead of U and V, now A and B here, and then you set W to be equal to 1. So this is a different R in this equation. Right. Now, if we assume that both R and T to be constant, what will happen is dr and dt should be equal to 0, and I guess you can understand that. Then you will have this equation right here, which is a very familiar one, and in fact it is the line element for the surface of a sphere, right? And this tells you that this metric is spherically symmetric as well. Now if the space-time is empty at a particular point, now if you think that you have a empty space-time, then what will happen is this energy momentum tensor at that point should be equal to 0, right? Remember that the energy momentum tensor is the component that have all the information about the energy, the source of gravity, right? Which leads to the curvature of the space. Now the curvature of the space is given by Riemann curvature tensor, and the source of gravity is given from this energy momentum tensor. Now if you are in empty space which has nothing, the energy momentum tensor should be equal to 0, right? Remember that after deriving the energy momentum tensor, we have discussed two specific situations where you have the dust only, and then it should be a perfect fluid. And this is another situation where when you have empty space, this energy momentum tensor should be equal to 0. And it is very important that you understand and remember these three situations, right? So it will come at different times. For the dust, you will have only one component for the tensor. And when you have a perfect fluid, which means you will have only the diagonal components of the energy momentum tensor. When this is an empty space, what will happen is we will have 0 for the energy momentum tensor because it's empty, right? Now, having all this information with you, so let's see how we can derive this Schwarzschild metric, right? So that will be our next task. So we have defined the form for the metric, but we don't know up to now that what is A, what is B, those kind of things, right? Our aim is that we should show that those A and B should be equal to the components that we have in the Schwarzschild metric, right? So that is our aim. And once again, what we did was we just wrote metric based on our assumptions and just check whether those assumptions are aligned with the metric. Now we are going to take that metric, and then there are components that we don't know, such as A and B, and we are going to solve in a certain way that so that we can find those metric under this condition, right? Now we will need that empty space for that as well. And let's go into a section where we can start solving this. And to solve it, we need to look at the field equations, Einstein's field equations in vacuum, and this is called vacuum field equations. And if we look at this carefully, what this means is in an empty space, we know that the energy momentum tensor should be 0, right? So what that means is, if you remember the Einstein's field equations that we derived last Monday, was that R mu nu minus half RG mu nu, then equal on the right hand side, there was the energy momentum tensor, right? But now in this particular situation, we are considering only the empty space, which means that component T mu nu should be equal to 0, which should be in the right hand side. So we make it to equal to 0, and you have this equation right here. R mu nu equal minus half RG mu nu, right? Now, from this, actually, you can prove that the Ricci tensor and Ricci scalar are also 0, right? And there is a simple way that you can prove it. So I have mentioned it here as a problem, which you can try. The things actually that I mentioned here as problems are simple calculations, and these are also based on the book, based on my reference book, and I have mentioned the section and the page number even here, so that you can go and look at the book, right? So the name of the reference book should be available in, I guess, in the LMS, and I have mentioned that book as well. But if anybody needs to find it, then please let me know, but you should be able to easily find it even in the internet. So that's why I put that reference book here. because you can find it. And if you go to this particular section of the book and the page number is also given, you can find this proof, right? And so this will also appear in one of your, if the time permits, I will try to prove it. But if not, this will appear in one of your tutorials, right? And remember, there will be another tutorial that I'm going to put into the LMS today or tomorrow. And so that tutorial will be based on everything that you have learned up to the last lesson, Einstein's field equations, where you have to do little calculations using geodesic equation and also calculate these connection coefficients and Riemann curvature tensor. Those kind of things will be included in that particular tutorial, right? And there will be another tutorial that comes in which have these kind of calculations, right? Now, as this problem suggests, actually you can understand that from this condition, we can prove that both Riemann curvature tensor, both Ricci tensor and Ricci scalar are zero, right? And you have to be very careful here, because having both Ricci tensor and Ricci scalar equal to zero does not necessarily mean that the space is flat, right? To have that condition, you have to take the Riemann curvature tensor and then prove that it is equal to zero, right? It is true that these two are equal to zero, but that doesn't tell you that the curvature is, zero, or you are in a flat space. So make sure that it is the Riemann curvature tensor is, the ultimate tensor that decide whether a particular space is, curved or flat. It is not these two guys, right? Right. Now we have the proposed metric right here. Now the things that I did up to here is kind of things that will be useful to derive the Schwarzschild metric, and this is how we derived it. So we have this proposed metric, and from that you can write the same metric in this particular form, right? So I have assumed a form like this based on those assumptions. So you will have d is squared e to the power 2x and then e to the power 2y, like that for those two components, right? For the time what you have for u and v. And actually these should be in fact a and b, right? So we derived a and b after this when w is equal to 1. So as you know that if a and b are functions of r, then both these components x and y should be functions of r as well. The reason that I have the exponential power here is that because they are positive, right? So when you take e to the power 2x dt squared, that is positive for sure. And then when you have minus e to the power 2y dr squared, that is negative for sure, right? So this is to keep that convention that for the metric, the first component is positive and all the other three components we write as negative values. So this, once you use these exponential powers in this way, you can keep that convention. So that is the idea. Now our task now is to find these x and y's, which are functions of r, because once you find those, then you are basically done. So you can take the e to the power 2x, and that should be basically equal to that component 1 minus 2gm over c squared in that Schwarzschild metric, right? So that is the idea. Now to get up to that point, we know that when you have these two components, e to the power 2x and e to the power 2y, the metric G0 term will be e to the power 2x and G11 will be e to the power minus 2y, and then G22 and G33 can be written in this way, right? So you can directly write these four values just looking at this metric, right? So these are the components in front of the coordinates. r theta and phi and t. And all the other values of this metric should be 0, as you know. It's only a diagonal metric. And when you have a diagonal matrix, it is easy to find the inverse as well. So what will you get is reciprocal values of those diagonal elements to the inverse metric, and all these 0 values will be 0 in the diagonal matrix as well. Right? So then you can write the diagonal element in this way. So I have directly written those here because we have done those before. Right. Now our next task is, now we know the matrix elements and we know which coordinate system that we are using, that is 4-dimensional space-time, spherical polar coordinates, so that we can find the connection coefficients using these metric coefficients G mu nu and G mu nu. You know that one is the normal metric and the other one is the inverse of that. So when you know that, you can use this equation which we have discussed before to find the connection coefficients, right? And I guess you have done 1 or 2 examples as well. And when you try to find the connection coefficients, actually there will be 40 independent connection coefficients for this particular situation. Now this is why doing calculations by hand in general relativity is a little bit challenging, right? So you have to calculate all these, but for this particular problem, you will only end up with having 9 of them as non-zero components, right? And these components will be these 9 components. I mean, there are actually more than 9, but you have only 9 independent components which you need to figure out. So there will be, like, some of these components will have the same value, right? So I have put it here as a problem for you to practice again. So you have to calculate all these connection coefficients, right? For example, if you take the first one, gamma 0, 0, 1. So what that means is, in this equation right here, sigma will be equal to 0. And mu will be equal to 0 and nu will be equal to 0. Now, when those 3 values are equal to 0, then you can see that when you take this component, the metric tensor component, sigma is equal to 0. So when this sigma is equal to 0, the rho is the summation index, right? So you can see that rho is inside the brackets as well. So that's like a summation index. You can decide which values that it can take. But the good thing here is, when sigma becomes 0, you know that our metric has only diagonal elements. So which means rho has to be 0 to have a value, right? So that's how you logically think about these calculations. Otherwise, if you start blindly just write all the components, everything will get messed up, because there are a lot of things that you have to add when you do it manually. Now, this is one very important thing when if you are given this kind of problem, even in an exam, you have to be careful in that way, right? Because if you start to look at all the components and try to write everything, then you will end up with losing a lot of time. And maybe if you lost your way at some point, it is very difficult to come back, right? Now, the way that, let me just maybe share this and show you how to do one calculation. It's not here, maybe. So let's do it in this way. I will finish the lecture today, but 1 or 2 examples I have given those in the tutorial as well. And I will probably have one of these calculations. 1 or 2 I will write at the beginning of the next lecture and show you how to approach for these kind of calculations, right? This is not difficult to do, but you have to be careful, right? So there are some points that you need to keep in your mind, like I told you, when you are trying to calculate the first connection coefficient 0, 0, 1. Now tau, the gamma sigma will be 0. So which means in this right hand side, this sigma has to be 0. So if you have, you can put that 0, but for the rho, you don't know what values to put, right? So rho can be 0, 1, 2, 3 because there are 4 indexes. But the thing is, for the rho has to be 0 in order to have a valid value, because when rho becomes 1, then you have G01 component, which is 0, right? Because you have only diagonal element in the matrix, right? When you have only the diagonal element, you have to take the advantage of that, because if you had the non-diagonal elements, then you have to sum up all those components to get the final value. So which will be a huge calculation at the end, right? So that is the point that I want to stress, but let me just take one or two of these and show you how you can approach it at least, right? And this is why it is important that you try this yourself. And I will even discuss within the tutorial as well, but the next day I will just show you one of those and how to approach that to find the connection coefficients, right? Now let's say you have done with this and found all these connection coefficients, right? So once you know the connection coefficients, then you can go for finding the Ricci tensor, right? Because there is a definition for the Ricci tensor. That's interesting. So I just want somebody, let me go back to right. So here is the Ricci tensor. Then you can find the Ricci tensor, which has this. This is the definition for the Ricci tensor. Once again, you have the same approach, and there will be 4 components that are non-zero when you write the Ricci tensor, right? So I have given that because for the other components, the values will be 0. And those 4 components are 0, 0, 1, 1, 2, 2, and 3, right? And those components will be non-zero. You can use this above equation right here to find the Ricci components. Once you know the connection coefficients, you can see that Ricci tensor is a function of connection coefficients. So that's why you first need the connection coefficients, and then you have to calculate these Ricci, the 4 components of the Ricci tensor. And then once you know the 4 components, actually the answers I have written here, but I have not done the calculation here. So I'm going to assign you as an assignment for you to try. And the advantage is if you try this yourself, you will get practice how to find these components, right? So it will be easy in your exams, right? And because I don't need that to explain the applications, what I need is the final metric only to explain you the different applications that you can have from this. So once you know the Ricci tensor, and this x dash and y dashes I have not defined earlier, because of that I have written it here. But if you go through the book, it has all these things written, right? So you can easily follow it up. So basically it's the same thing here. And I have an assignment for here. Use the vacuum solution where all components of Ricci tensor are 0, and principle of consistency to prove that, yes, there is a delta sign here. So I should remove, right? To prove that e to the power 2x will be equal to this component right here, and e to the power 2y will be equal to this component, right? And I have written here, you may refer to chapter 9 of the book because it has all this derivation, right? So I have taken all the information from that. So I would highly recommend that you do it. If everyone completes, maybe at the end we will discuss about that, right? This is a very nice exercise that you can be happy yourself that you know how to do these calculations and work with these metric tensors, right? Which is nice. And I have guided you throughout this note to that direction, how to do that. Now you can use that knowledge, even the knowledge that you had from the previous lesson, to show that in the Schwarzschild metric, these first two components are these two, right? Based on those assumptions and the calculations that you do, right? The part that you have to do here is actually to work with the Riemann curve, work with the connection coefficients and the Ricci tensor. And once you do those two, with the previous problem that I showed, that I asked you to show you that when you are in a vacuum field, which is for the vacuum solution, the energy momentum tensor should be 0, and because of that, both Ricci tensor and the Ricci scalar should be 0. So what you are going to do at the end is actually you take this Ricci scalar and Ricci tensor. So you first write the connection coefficients and calculate the connection coefficients. Once you know the connection coefficients, you can prove that these four Ricci scalar values, these four components of the Ricci tensor, so the Ricci tensor are these values right here. Once you know these components of the Ricci tensor, you can use that result that you are going to derive, that for a vacuum solution, where the Einstein's energy momentum tensor is equal to 0, all these Ricci tensor components should be also equal to 0. You will be proved, you have proved it earlier, and then you can make all these four components equal to 0, right? Now, when all these components are equal to 0, you can equate each other to find these coefficients, right? And then there will be one or two terms that are, I mean, there are some terms that you cannot find alone just using these relations. For that, you are going to use the principle of consistency. What that means is that field equations will be reduced to Newtonian gravity under certain conditions. So you can use that reduction to complete the proof, right? Now, all these things are in chapter 9 of the book. So I want you to, based on the information now I have already provided, just go through and read that sections and try to complete this assignment, right? So I expect that all special degree students, you can try this, right? And we can actually discuss at the end if the time permits. But this is for you to practice. So if you practice, this will be good for you in exams, right? And you will realize that this calculation is little bit harder, not harder. Actually, you have to do a lot of calculations here for this particular one. But once you do something like that, the simple ones will be easier to calculate, connection coefficients and those kind of things. And I will give you some of, I do not have the facility today, but I will show you one or two, like how to approach to find these connection coefficients, and also for the Ricci tensor, those kind of things on the next day, right? So that's it. And then we can come back to the presentation. Yeah. So you have four non-zero components, 0, 0, 1, 1, 2, 2, and 3. And those components are written here in terms of x and y's. And there is x dash as well. And I have defined what x dash is and what u is, because this will be important for your assignment that I have assigned. And this is the assignment once again. Right. So once you complete up to this point, you can realize that you have proved that your Schwarzschild metric should have these components, right? But for you, even though you cannot understand this whole process, what I am going to do in the next section is use the Schwarzschild metric to define different, look at different applications, right? So let's directly take the Schwarzschild metric. So we will discuss some of the important implications and the properties of Schwarzschild space-time here, which is basically using the Schwarzschild metric. And apart from that, I expect to talk with you these four situations, which we normally consider as the four classical tests for the general theory of relativity. There is a mistake in the words here. Four classical tests in the general theory of relativity, and that will be about the gravitational shift, redshift, and we are going to talk about the precision of the perihelion of the Mercury. So that's a nice application of the theory of gravitational theory by the Einstein, and the gravitational deflection of the light, how the light is curved near, we normally used to tell that the light goes in a straight line even in A-level physics, right? I mean, don't go and tell to an A-level student that the light is bended. I mean, it's a straight line under normal condition, right? But when you consider about these, the huge gravitational sources such as, black holes and those kind of stuff, actually the light bends around that. Right? That's what happens, and we will talk about that a bit. And then gravitational time delay of a signal passing of the sun. So this is one of the experiments, or one of the instances that we proved that the Einstein was right in this general theory of relativity. Right? So we actually will discuss all these situations. And to start with, let me start with the Schwarzschild space-time. Right. So basically, remember that I told you the Schwarzschild radius is written in this way: Rs equal to Gm over c squared, which can be also written as equal to 2 times m, when you assume that Gm over c squared will be equal to m. I think we have done it in the Schwarzschild metric as well. And capital M is the mass of the spherically symmetric gravitational source, so that this could be a black hole, our own sun, or something like that. And then the metric can be also written in terms of the Schwarzschild radius, which we have done before, so I am not going to talk about that again. So that, remember once again, that previous section that I have talked is how to derive the Schwarzschild metric, right? First, you define some of the assumptions, and based on the assumption, you write a metric which has components that you don't know, and then you use the connection coefficients and the vacuum energy solution of the Einstein equation to find those. You use those vacuum energy solution and the connection coefficients, then the Ricci tensor and the components of the properties of the vacuum energy solution to find those components of the Schwarzschild metric, right? So what we are doing is just using the Schwarzschild metric for different applications. So make sure that you understand those two situations separately. And you can see that if the mass goes to 0, R is, if M goes to 0, which means the R will be equal to 0, as you know, right here. So if M goes to 0, this Schwarzschild radius will also go into 0. And so when this happens, Schwarzschild metric reverts to the metric of special relativity expressed in spherical coordinates, right? So that is when this mass goes to 0, which means you don't have a gravitational source. When that happens, the Schwarzschild radius will become 0. And when the Schwarzschild radius will become 0, you can see that in this equation, you just do not have this minus component right here. So you just have c squared dt squared. And here when Rs goes to 0, you just have dr squared, and then r squared d theta squared minus r squared sine squared theta d phi squared. And every one of us know that is the Minkowski space, so flat space metric in spherical coordinates, right? And that happens when m is equal to 0. M is the the mass of the spherically symmetric gravitational source. And this again tells you that when you do not have a gravitational source which can curve the space-time, the space-time will be flat, right? And you can represent it from the Minkowski metric, right? So that's how you interpret it. Right, there is a question for you, and the time is 7:40. So I want an answer from you before I continue from this point. And this is not a difficult calculation. Assuming that both the Sun and Earth are spherically symmetric bodies, calculate the Schwarzschild radius of those two objects. Now, can you do this calculation for me so that we can continue from here? So all you need to know is the mass of the Sun and the mass of the Earth and the value of the gravitational constant to find the Schwarzschild radius, right? Once you find the answers, those two answers will be very interesting for us to continue, right? Now, so there are sources, even in the internet, you can find the mass of the Sun and mass of the Earth, and then the value of the gravitational constant. So all you need to do is plug those values here for G and M, and then C squared, and then find the Schwarzschild radius, right? So I want you to find the Schwarzschild radius for the Sun and Earth, which are spherically symmetric bodies. And once you have those two values, that values itself tells us a story, right? So I want those two values to continue from this particular point. So therefore, I would like you to calculate do this simple calculation and come with the answer. And would you like to do it now? Because this is not a hard calculation, right? So only thing is you need to find the value of the mass. Okay, now okay, let's do it in this way. Now it's 7:45. So let me stop from here. So please do calculate the Schwarzschild radius for those two objects. And for sure, all of you should be able to do this calculation, right? And it is very important that you can do this. Make sure that you do the calculation and come up with the Schwarzschild radius values for the Sun and our own Earth, right? And based on those two values, we will talk a little bit more on the next day about the Schwarzschild, the metrics, and then there is something called singularity. And this you probably have heard about this word singularity in mathematics and well as in physics, especially when you talk about black holes, right? And we will talk about that on the next day. And then after the singularity, we will go and talk about gravitational time dilation. And we will prove an equation to show how the gravitational time dilation works. And then moving to the next section about the gravitational redshift, right? Anybody have any questions up to here? කාටද ප්‍රශ්නයක් තියෙනවද අහන්න? Right, so if not, let me stop from here, but just take the next 5 to 10 minutes and do the calculation for the Schwarzschild radius for the Sun and for the Earth, right? And come up with that calculation. And once I start the lecture on the next day, make sure that you post your answers to the chat window on the Zoom. And after that, we will discuss the lesson further from that point, taking those two values, right? So that is the plan. And I think we are gradually coming to the place where we plan to. So that is after discussing about the gravitational time dilation and gravitational redshift, and also this deflection of the light and those kind of, these are actually also considered as the test for the special relativity, that how you test whether the special relativity is correct or not. And after that section, which I plan to finish on the next day, I will be start talking a little bit more about black holes, because we have not talked about that under the astronomy, different types of black holes, which we can actually use the knowledge now we have about the Schwarzschild metric and the field equations to apply for that. And the last section of your lectures is very important. That is about the cosmology of the universe, right? And under that, we are going to talk about a new metric called Robertson-Walker metric. And based on that, we are going to derive, if time permits, the set of equations that we called as Friedmann equations. That is, again, you write the Robertson-Walker metric and then find the connection coefficients, Riemann curvature, Ricci-Tensor, and Ricci scalar, and use those together with the energy momentum tensor to write the Einstein equation and solve it, right? Even without solving, we can actually discuss about the solutions in a different way. And this will allow us to find what kind of universe that we are living and what will be the future of us, right? And together with that, I'm going to talk about the Big Bang theory, which is about, which basically talks about the beginning of the universe, and all these things will be connected in the last set of lectures, right? I guess we have around, this is probably the end of the 11th week as far as I remember. So there are around roughly 12 lectures to go, 10 to 12 lectures to go. So maybe most of the lectures will be, devoted to this cosmology part. And then at the end, I will discuss all the tutorials that you have, right? So that will be the plan. Right, anybody, if you do not have, anybody have any questions once again? Right, so if not, let me stop from here and we will meet again, most probably on Monday. And if the time changes, I will let you know ahead of time, right? So I may have to change the time for the next week because of some of the other meetings. So I will let you know about that probably tomorrow or day after tomorrow. Right, so thank you for everyone and for joining, and we will meet again next week to discuss the next section.